There's lots of roadworks in the street, so there might be some background noise, but let's run this tiny program anyway. I've set things up so that I've got a program loaded, and my registers initially show that the loop index is 3. So that might be a clue that there's a loop in our future. Let's get cracking. The instruction pointer is 0, so we're starting at the start of memory where we find the operator B, and B decodes as clear carry flag. Now if we look at the flag register, we can see the carry flag is already clear, so that's going to stay 0, and the instruction pointer will move on to 1. At location 1 we have a 6 which decodes as get. So we look at the input queue and we see the first input is 3. So I'll record that in the trace, and then I will update the registers. The 3 arrives in the accumulator. 3 is not 0, so the 0 flag stays 0, and the instruction pointer moves on to 2. Ooh, clumsy. Now what's at location 2? A for add with carry, and the operand is here at location 3, and that's E, which tells us where to find what to add. So what is in location E is a 0, and that's nice and easy. We have to add 0 to 3 with a carry flag of 0. That's going to give us 3, which doesn't carry, there's no overflow, and 3 isn't 0, so the flag register stays 0, and the instruction pointer moves on to 4, which is great. What's at 4? We've got STA, again with operand E. So that's to say we're adding on the input to what was in location E and then updating E with the running total. Let's do that. E now becomes 3. And the instruction pointer moves on to 6. What's at 6? Another 6, which is another get. So what's our next input? It's a 2. Record that in the trace. Bring it into the accumulator. Check. 2 is not 0. 0 flag stays clear. Instruction pointer moves on to 7. And what's at 7? Another A for add with carry. This time with operand F. It's almost like the same thing's happening again. What's at F? Another 0. So we've got a nice easy problem again. 0 plus 2 plus a carry of 0 just gives us 2, and we don't carry. 2's not 0, we don't overflow, and the instruction pointer moves on to 9, where you've guessed it, we store the result back to F so that we end up with a 2 here, and the instruction pointer moves on to B. Now, what's at B? That's a D. And D stands for decrement the loop index. The loop index is currently 3, so if we decrement it, we get 2. Is 2 0? No, it's not. So the 0 flag stays clear, and the instruction pointer moves on to C. What's at location C? Operator number 3. That's jump, if not 0, with an operand of 0. And as the 0 flag is clear, we're being sent back round to the start of the program. So what I'm going to do is just touch up the loop index and the values stored in E and F. They are now 3 and 2. And I'll go round the program again. It's actually the same program as before. We've seen no self-modifying code. So we've done the D code already. All that's going to happen is that the inputs and the arithmetic will be different. So when we get to this first get, we will now receive the input E. So this will be an E, which is still not 0. And when we do the add with carry, what we will be adding is this E plus the contents of that E plus a carry of 0 from clear carry flag, and that's E plus 3. What's that? 14 plus 17. That's 1, 1 in hexadecimal. So we have a 1 here, carry 1 into the carry flag. We should also think, is 1 0? No, it's not. Does E plus 3 overflow? Well, E's negative, 3's positive, no overflow. So that just means we have a carry of 1 going into the flag register. Okay, and that E is gone from the input queue. So then when we store, that puts a 1 into the running total, but we have a 1 in the carry now. So when the next get happens and gives us a 3, that goes into the accumulator, and we still have a carry of 1, but at least 3 isn't 0. Now when we do the add with carry, what are we computing? We are computing 3 plus the contents of F, that's 2, plus the 1 in the carry flag, gives us 6. With no carry, 6 is not 0, and no overflow. So what just happened there? Well, it gets stored back into F. So now we have a 6. So what's just happened? We've added some more inputs onto our running total. And moreover, there was a carry from the first addition into the second, which suggests that location E is the little end of a 1-byte number and location F is the big end. So what we've just done is added a 1-byte number onto our running total by doing 2 4-bit additions carrying from the low end to the high end. So what we're doing is making a running total of numbers that come in 2 hexadecimal digits at a time. Okay, so we decrement the loop index. Oh, before that, I should make sure I've crossed off my input. We're decrementing the loop index, and that goes down to 1, which is still not 0. So we're going around again. That was a messy jump cut, but I've taken the opportunity to clean up the board, ready to do the last iteration of the loop. We have 1 in the loop index. So what happens, as ever, we clear the carry flag to get ready to add, but it was already clear. And then we get our next input, that's for the little end, and that's a 1. Okay, our add with carry adds this 1 onto the running total of 1 with no carry coming in, and that gives us going too fast because I'm in a panic. that was a messy jump cut, but I used the opportunity to clean up the board, ready to go around again. The loop index is still 1 from last time. We've got 2 inputs left in the queue, and our running total is 1 at the little end and 6 at the big end. We have clear carry flag, which is to get us ready for the next round of addition. The carry flag was already clear as it happens. And then we get the next input, that's a 1. So the 1 goes in the accumulator, 1 is not 0, flag register stays 0. And now we do our next addition. Our running total in E has a 1. We have a 1 coming in and no carry, so that's going to give us 2. No carry, no overflow, no 0. And that 2 at the next instruction gets stored back into the running total in position E. We get our next input, that's a 7 coming in for the big end. So that goes into the accumulator, and again 7 isn't 0. Our add with carry will then add the 7 onto the running total in location F, which is 6, and a carry of 0. 7 plus 6 is 13, that's D in hexadecimal. And there's no carry, and D is not 0, but hang on a minute, in 2's complement 4 bits, 7 and 6 represent positive numbers, but D represents a negative number, so overflow has occurred. The flag register becomes 4. Even so, this D gets stored to location F. And we arrive back at our decrement loop index. Loop index is currently 1, so that is going to go down to 0. And because we've just made the loop index 0, that's going to set the 0 flag. That means the flag register will go from 4 to 6. And now when we see jump if not 0 to 0, the 0 flag is set, so we don't jump. At which point we run slap bang into the values that are stored as our running total, 2 and D. And as I've given the game away, that's actually an instruction, jump if 0 to location D. So the 0 flag is set, and what happens is that we end up in location D. Instruction pointer is at D, and what's at location D? 0. So that gets interpreted as a halt instruction. What an outrageous coincidence. The instruction pointer goes up to E. The halt flag gets set, which means the flag register becomes E. And we're done. What have we seen? A loop with 3 iterations done with decrement loop index and jump if not 0, which computed a sum of 8-bit numbers with a little end and a big end and carrying in between. And by an outrageous coincidence, we computed an instruction that would enable us to stop.